Swayam Prabha. Digital India. Educated India.
Welcome friends to this third lecture of module 2, that is inorganic soil components. And in previous two lectures we have discussed about different types of crystallographic structure as well as the Pauling's rule and 5 different Pauling's rule and how they impact the stability of different crystallographic structures, and we have discussed about the coordination number. And also we have briefly discussed about the classification of the soil silicates. We have discussed about the difference between primary minerals and secondary minerals. Now in this lecture we will be discussing in details about the primary minerals and also the secondary different types of secondary minerals. So when we talk about the primary minerals, the first mineral which basically comes to our mind is basically the feldspar. Now, feldspars are anhydrous 3-dimensional aluminosilicates of linked silica tetrahedra and aluminum silica tetrahedra and aluminum tetrahedra that contains the cavities that can hold the calcium, sodium, potassium and barium to maintain the electroneutrality. Remember that these feldspars are the most common primary minerals in the earth crust, and they are basically found mainly in sand and silt fractions, and they are basically non-reactive in nature, and the potassium bearing feldspars are the major source of potassium in soils. So, if we see the classification of the feldspar, there are two major types. One is called the alkali feldspars and another is plagioclase feldspars. Now, alkali feldspar, their composition ranges from this potassium feldspar to sodium feldspars, and plagioclase feldspar, their composition ranges from sodium feldspar to calcium feldspars. So, if you see some examples, obviously potassium feldspar, the examples are either orthoclase or microcline. These are two major examples of potassium orthoclase, potassium feldspars, whereas sodium feldspar example is albite. So, remember again, the feldspar is the most common and most widely abundant mineral in the earth crust. The second most abundant mineral in the earth crust is quartz. So, quartz is basically a hard crystalline mineral which is composed of silicon and oxygen atom, and the atoms are basically linked in a continuous framework of SiO4 silicon oxygen tetrahedra, with each oxygen being shared between the two tetrahedra, giving an overall chemical formula of SiO2. We have discussed this tectosilicate structure in our last lecture when we have discussed about the classification of soil silicates. Now, this quartz basically an example of this tectosilicate, which is basically a 3-dimensional and stable structure. So, quartz is also the second, as I have already told you, the second most abundant mineral in the earth continental crust behind the feldspar. This is an example of the quartz mineral. Now, there are some other accessory minerals also which are found in heavy specific gravity fractions. Some examples are olivine, pyroxenes and amphiboles. You can see that pyroxene and amphiboles are ferromagnesian minerals, that means they basically contain iron and magnesium with single and double chain structure respectively of linked silica tetrahedra. So, basically they represent the inosilicates, which basically shows the single or double chain of tetrahedra. Now, olivine, as you know, it is basically a nesosilicate. They are basically green nesosilicate within which the magnesium and iron, since they are ferromagnesian minerals, obviously they will contain iron and magnesium, are octahedrally coordinated by oxygen atom. And remember one important fact, that these olivines, that the ferromagnesian minerals are the major source of magnesium and iron in the soils, and remember these magnesium iron are the major micronutrient for plant growth. So, some examples are given here, like tremolite is an amphibole which has this formula, and it is also contain the calcium and magnesium. Pyroxene examples are given like instatype, diopside and rhodonite. The formulas are given here. Olivine formula, as you can see, it is a ferromagnesium minerals, so iron and magnesium are there, and this is the formula of olivine. So, let us see some pictures of this mineral. This is an example of tremolite. As you can see, this is diopside and olivine, all these are primary minerals. So, all these primary minerals basically forms the skeleton of the soil, that means the sand and silt fraction. And whenever we go from the primary minerals to the secondary soil minerals, the chemical nature gets changed. Remember, these primary minerals maintain their chemical composition irrespective of their size. They maintain their original chemical composition from the rocks from which they developed. However, when the chemical composition changes from one mineral to another mineral, the secondary soil minerals basically appears. The another name of secondary soil minerals are secondary clay minerals. We have already discussed about the phyllosilicates, which are the major one of the major class of the soil silicates and also known as the soil clay minerals. So, apart from phyllosilicates, the secondary soil minerals also consist of interstratified clay minerals, oxide, hydroxide, oxyhydroxides, and also carbonates and sulphate minerals. So, as you can see, you are seeing here the structure of the phyllosilicates with the basic structural formula of Si2O5, and now we will see different types of phyllosilicates. So, phyllosilicates, as you know, the secondary clay minerals or simply the clay minerals are the best example of phyllosilicates, which occur primarily in the clay size fraction. Why they are called clay minerals? Because they are occurring in the clay size fraction, and they play a major role in various soil chemical reactions. Clay minerals, remember, they are the assemblages of tetrahedral and octahedral sheets. Basically, they are combination of different tetrahedral sheet and octahedral sheet in different stacking fashion or different stacking arrangement. And remember that the clay minerals are, the tetrahedra are bonded point to point, which we have already discussed, and whereas the octahedra are bonded from edge to edge. So, it is basically characterized by the typical layer or sheet like structure. Remember, the phyllo means phylum or leaf like structure. So, the name came from this leaf like shape. So, this is the clay minerals. As you can see here, this is a structural unit of the phyllosilicates. So, let us start with the discussion with the first one building block, the first building block of soil, that is silica tetrahedra. Now, silica tetrahedron, you can see the aluminum, the silicon cation is surrounded by 4 oxygen anions, and the internal angle is 109 degree. So, when these individual silica tetrahedra share their oxygen between two adjacent tetrahedra, they form the shape, sheet like structure, and we call this a tetrahedral sheet. Now, as you can see here, this is an individual tetrahedral sheet, and this is this is the individual silica tetrahedra 3-dimensional figure, and this is basically the tetrahedral sheet which is generated by sharing their points. So, let us see how they basically join together. So, these are the individual silica tetrahedra. So, silica tetrahedron. So, when this individual silica tetrahedron comes together and share their oxygen, the corner oxygen, then they basically form this sheet like structure, and it is known as the tetrahedral sheet. This is the tetrahedral sheet. Similar in case of aluminum octahedra, you know that aluminum octahedra is basically composed of aluminum at the center surrounding by 6 hydroxyl anions forming a octahedral like shape. So, when these octahedral share their edges, they form this octahedral sheet. So, let us see, this is a single aluminum or magnesium octahedra, and when they share their edges, they will form this structure called octahedral sheet. Now, this tetrahedral sheet and octahedral sheet are the basic building blocks of any clay mineral structure, because all the clay minerals are basically, most of the crystalline clay minerals are basically developed by a specific stacking arrangement of this tetrahedral sheet and octahedral sheet in a single clay crystal. So, if we see the overview of a clay mineral structure, we will have this picture. So, let us discuss how these different sheets, that means octahedral sheets and tetrahedral sheets, join together to form a total clay mineral lattice. So, as you can see that a tetrahedral sheet, this is basically a 2:1 type of clay mineral. Why it is called a 2:1 type of clay mineral? Basically, because you are seeing that there is a one octahedral sheet which is sandwiched between two tetrahedral sheet. So, that is why it is known as the 2:1 type of structure. Now, in the 2:1 type of structure, as you can see how they are joined together. So, this is basically a tetrahedral sheet. If you consider the tetrahedral sheet inverted, then obviously the basal cations will be basal anions will be oxygen plane. So, the basal plane will be basically oxygen plane, followed by this silicon plane, which is the major cation, and the apical oxygen for each of these tetrahedra will be basically shared with this adjacent octahedral sheet, and this adjacent octahedral sheet is basically composed of this aluminum and magnesium plane in the middle, and in this shared layer it will be basically either oxygen or hydroxyl. So, as you can see, this is hydroxyl and oxygen will be shared between this tetrahedral sheet as well as this octahedral sheet. The similar thing will be repeated here also. So, this is how we will get a total 2:1 type of structure. So, basically one thing is clear, that to join two different sheets, we need to they need to share their apical oxygen, specifically the apical oxygen of the tetrahedral sheet, and that is how they join. So, obviously based on this structure, they will get an O plane followed by a silicon plane, and then they will get an O, that means oxygen as well as hydroxyl plane, followed by aluminum and magnesium plane, then again oxygen hydroxyl plane, then again silica plane, and then followed by an oxygen plane. So, as you can see, this basically defines how this 2:1 structure is composed of. Now, in the clay crystal, this individual layer is repeated several times, thousands and thousands times. So, this individual layer will be stacked over another individual layer, and ultimately they will create this clay crystal, and the space between these individual layers are known as basically known as the interlayer space, and this interlayer space is the area where they absorb basically absorb different types of cations and water. So, this is the basic structure of a clay mineral, 2:1 type of clay mineral. Now, when we call it as 1:1 type, obviously when there will be one tetrahedral sheet and one octahedral sheet, it will be called a 1:1 type of clay mineral. However, since here the octahedral sheet is sandwiched between two tetrahedral sheets, it is known as the 2:1 type of clay mineral. So, phyllosilicates nomenclature, as I have just told you, that phyllosilicates nomenclature based on the number of tetrahedral sheet and octahedral sheet joined together. As you can see here, the 1:1 layer is basically composed of one tetrahedral sheet and one octahedral sheet, whereas 2:1 layer is basically composed of one octahedral sheet sandwiched between two tetrahedral sheet. So, what are the basics of distinguishing crystalline silicates clays? There are several criteria based on what we can distinguish different types of crystalline silicate clays based on the number and combination of structural units, that means tetrahedral and octahedral sheets, planes combined, sheets combined, layers and crystal, which we have seen just. And then there are two different general categories like 1:1 and 2:1. There is an intermediate category also, we know it is known as the 2:1:1 or 2:2. Example is chlorite, we will see it in our lecture. And also based on the number of cations in the octahedral sheet. So, either it is a trioctahedra or dioctahedra, depending on size and location of layer charge, depending on the type of bonding between the layers, because you know that there are different types of bonding like ionic bonding, then hydrogen bonding, van der Waals bonding. So, based on these different types of bonding and their strength also, we can distinguish different types of silicate clays, and also based on the absence or presence of cationic interlayers, we can also distinguish different types of clay minerals like fine grained mica. So, let us first discuss the types of clay mineral. Obviously, as you know that there are two main groups of crystalline clays, 1:1 type of clay, and which is basically composed of one octahedral and one tetrahedral, and basically this is the structural formula, where this 4 denotes basically the tetrahedral coordination and 6 denotes the 6-fold coordination for this aluminum, or octahedral coordination for aluminum. And the 2:1 type of clay, where one octahedral one octahedral sandwich is one octahedral sheet sandwich between two tetrahedral sheet, will get a formula like this, where the silica will show the tetrahedral coordination, aluminum will show the octahedral coordination. And this is basically shorthand representation of this 1:1 and 2:1 type of mineral. So, one more thing comes into our mind while we discuss about the structure of clay mineral, that is dioctahedral and trioctahedral. You will encounter these terms frequently in the coming slides while we discuss the different types of clay mineral structure, dioctahedral and trioctahedral. So, what is the difference? Now, remember that clays can be divided into di and trioctahedral depending on the number of cations, number of cationic positions in the octahedral sheet that are occupied. For example, if aluminum is present in the octahedral, only 2/3 of the cation positions are filled. If we go to the next slide, it will be more clear. So, this is an example of a trioctahedral structure and this is an example of a dioctahedral structure. Now, you can see this is a tetrahedral sheet, this is another silica tetrahedral sheet, and this is an octahedral sheet sandwich in between. So, the octahedral sheet has 3 octahedral positions, 1, 2, 3. Here you can see 1, 2, 3. So, if all the octahedral positions are filled by cations, then it is called the trioctahedral structure. Example is phlogoptite, and remember one thing, that if there is a divalent cation present like magnesium, then it will give this dioctahedral structure. And if 2 out of these 3 octahedral positions are filled due to the presence of aluminum, that is Al3 plus, then we will see this is a dioctahedral structure. So, this is called a trioctahedral structure, this is a dioctahedral structure. Example is muscovite. So, this is the difference between trioctahedral and dioctahedral structure. So, for every 6 hydroxyl ions, 2 aluminum ions satisfy the anionic charge, as aluminum 3 is trivalent, which you have just seen here. So, that is why it is called dioctahedral. And if magnesium is present in the octahedral sheet, 3 of them would satisfy the anionic charge of 6 hydroxyl ions, hence it is called the trioctahedral, which we just have seen. So, this is the difference between dioctahedral structure and trioctahedral structure. Now, another important feature we want to discuss, that is called the isomorphous substitution. Isomorphous substitution means a substitution of one atom by another atom of similar size in a crystal lattice without disrupting the crystal structure. So, let us consider an example that a cation with a coordination number of 4 can substitute silica in tetrahedra, and a cation of coordination number of 6 can substitute aluminum in octahedral sheet without disrupting the crystal structure. And the first and foremost criteria for doing that is they have to be almost similar size, and that is why this phenomena is known as isomorphous. Iso means similar, morphous means similar in morphology or similar in size. So, a silica can be substituted by another cation in a tetrahedral coordination which can show a coordination number of 4, for example, aluminum. So, aluminum can replace silica in a tetrahedral coordination and still maintain its structural integrity, because aluminum has almost similar size than almost similar size as of silica. Similarly, in octahedral layer, aluminum gets replaced by either Fe2 plus or Mg2 plus, and because they have the similar coordination number of 6. So, this type of substitution is known as isomorphous substitution. Now, what is the implication of this isomorphous substitution? Remember, when we are substituting a ion cation with another cation of different valency, that means in case of tetrahedral sheet, when we are substituting a silica cation which has 4 valency with aluminum cation with 3 valency, then obviously there will be a charge imbalance. That means we are reducing the positive charge, that means we are increasing, in other way we are increasing the negative charge development. Okay. So, this charge imbalance basically develops due to this isomorphous substitution, and this charge is also known as the permanent charge, because this is the feature of its crystalline structure. It is not variable. So, that is why this charge which is developed due to its structural arrangement or isomorphous substitution is known as a permanent charge. So, when aluminum replaces silica in a tetrahedral sheet or tetrahedral coordination, a charge of -1 is created in an 1:1 type of clay. Obviously, silica is 4 valence, aluminum is 3 valence. So, when they are replacing each other, there will be one negative charge generation. So, this thing will be more clear here. As you can see, this is a trioctahedral structure, where this for example, let us consider this is a magnesium with 2 valency. So, 3 magnesium will satisfy all the 6 anions, and so producing a net negative charge. So, all 6 anions are basically, as you can see, it is 3 negative here, 3 negative here. So, 6 negative and 6 positive from 3 cations. So, we are getting a net charge of 0. Okay. In case of dioctahedral, obviously, as you know, 3 out of 2 positions are filled, 2 out of 3 positions are filled by aluminum. So, as you can see here 3 plus and here, so 6 plus and 3 minus. So, 2 aluminum will be required to satisfy the charge to get a net charge of 0. So, when this isomorphous substitution occurs in this octahedral sheet, suppose we are replacing one aluminum ion with one magnesium with the valency of 2 plus, we will get a dioctahedral structure with isomorphous substitution. And when we are getting a dioctahedral structure with isomorphous substitution, obviously here total positive charge is +5 and total negative charge is -6. Ultimately, we are getting a excess of negative charge. Why we are getting this substitution? Because you can see here aluminum and iron and magnesium has similar, almost similar radius. So, this is called the isomorphics or isomorphous substitution, and isomorphous substitution is the reason behind producing the negative charge in the clay mineral, and that is why clay mineral is very reactive. The sand and silt are not reactive because they are electroneutral. However, due to the presence of this type of negative charge on the surface, the clay minerals are highly reactive. So, let us start with discussing different types of clay minerals. Let us start with the 1:1 type of clay, which is called the kaolinite and serpentine group. So, basically it is called 1:1 type of clay because it is composed of one tetrahedral sheet and one octahedral sheet. So, one tetrahedral sheet, one octahedral sheet linked together to form this 1:1 type of layer by sharing their apical oxygen atom, and it can be divided into dioctahedral kaolins as well as trioctahedral kaolin. As you can see here, the examples are dioctahedral kaolin or kaolinite, dikite, nakrite, halloysite, and also we can see some trioctahedral kaolin, and their composition that is half cell chemical formula unit are also given here. So, this is basically the kaolinite structure, one silica tetrahedral sheet and one aluminum octahedral sheet. So, one silica tetrahedral sheet and one aluminum octahedral sheet are basically joined together by sharing the apical oxygen. Here you can see sharing the apical oxygen of the tetrahedral layer, and then it is following this layer structure of 1:1 layer structure. The one thing is very clear from this structure that these two adjacent layers, so this basal layer from this so the basal plane of atoms is basically representing hydroxyl here, and the next layer of atoms in this next layer, adjacent layer, is basically the oxygen atom. So, you can see hydroxyl ionic layer is basically coexisting with the oxygen layer, and as a result of this difference in their electronegativity, there will be formation of hydrogen bonding. As a result of this hydrogen bonding, the interlayer space between kaolinite is very limited, and that basically explains why kaolinite is it is nutrient poor. We will discuss that later, but one thing is clear from this structure that one tetrahedral layer share their apical oxygen with the octahedral layer, producing a 1:1 layer structure, and when you compare, when we see the two adjacent 1:1 layer, we will see the coexistence of or close existence of one hydroxyl atomic layer with one oxygen atomic layer, producing the hydrogen bond. So, as a result, their interlayer space is basically collapsed, and when the interlayer space is collapsed, there is no chance of getting other ions in the interlayer space. And so, the kaolinite is most common in it is one of the the kaolinite is the most common 1:1 dioctahedral kaolin, and it is basically synthesized under equal concentration of aluminum and silica. You know that it has got little or no isomorphous substitution. So, there is no negative charge, excess negative charge development here, because there is no isomorphous substitution in case of kaolinite. As a result of that, there is no shrinking and swelling properties in kaolinite because of hydrogen bonding between the adjacent layers, and that is why this type of mineral kaolinite is nutrient poor, and the ideal full cell chemical formula is given here. So, another important mineral is called halloysite, which is a 1:1 dioctahedral kaolin, and this has the similar structural unit than as we have seen in case of kaolinite. However, only difference is it has got an interlayer water, there is interlayer water molecules. So, basically there is a layer of water molecules in the interlayer space in between this 1:1 layer. So, drying, when we dry this water, this mineral basically collapse and produce a tubular like structure, a tube like structure because of rolling. As a result of dehydration of this water layer from this interlayer space, the hexagonal plate like structure will basically roll and produce this tubular like structure, and this tube like structure is the most distinguishing feature of halloysite. So, guys, we have discussed about different types of primary minerals. We have discussed about we have started discussing about the different types of secondary minerals. We have discussed how this 1:1 layer and 2:1 layer basically forms, and we have started discussing about the individual clay minerals. We have completed kaolinite and halloysite, and in the next lecture we will start discussing about 2:1 type of clay mineral. We will be discussing pyrophyllite, we will be discussing talc, we will be discussing illite, mica, vermiculite, and 2:2 type of clay minerals, and other types of clay minerals and other types of secondary minerals we will be discussing. So, thank you for your attention, and let us meet our next lecture to discuss the rest of the clay minerals. Thank you very much.